In this video, we are going to talk about enzyme kinetics and complete our discussion of enzyme kinetics and talk about the regulation of enzyme activity and how we can use kinetic measurements to figure out what's going on with our enzymes and how their activities may change based upon this. All right, so I'm going to start by reviewing what we talked about in lab when we introduced the concept of enzyme kinetics. So remember, okay, that all of our mathematics is based on a conceptual model of enzyme activity, okay, or enzyme action. So these are the steps. Okay, not the steps as in detailed catalytic mechanism, but the steps that have to happen in a global sense. And what I mean by that is that in this model, we have one substrate molecule that binds to one enzyme molecule. They have to form a bound complex, and then that bound complex can either diffuse apart or we can get product made. And so each of these steps can have a rate associated with it. Okay? And so if your rate of dissociation is more than your rate of product formation, you're not going to see a whole lot of product happening, right? So we made certain assumptions about, for example, this reaction right here essentially being irreversible. So much favored in the forward direction that we don't really see enzyme and product, recombining to form an enzyme substrate complex. And then we made the assumption that we would do our experiments at a steady state, right? So we would set up the concentrations of the reactions in such a way that we're looking at our rate here. Okay, so we're going to look early in the reaction, okay, but once we have kind of achieved like a condition where we have sort of a constant rate or a constant concentration of the complex, okay? And so we're not going to look, the instant we mix. We'll look, a few microseconds after that, so that we get to this point. And we're not going to be taking our measurements over here where we've really depleted our substrate concentration. We have kind of nothing left, right? All right. So we have a conceptual model. We set up our experiments so certain conditions apply, and then we derive, okay, based off of things like equilibrium constant expressions and rate expressions. We derive what's known as the Michaelis-Menten equation. Okay, so the Michaelis-Menten equation, okay, relates the rate of the reaction, the velocity of the reaction, okay, so that's that right there, to the substrate concentration, right, and the affinity for substrate, which we call the Km, right, and we said it's not exactly a Kd for the substrate because it takes into account the fact that you have this other process here where you can get your enzyme substrate complex disappearing in two ways, right? It can disappear via the substrate diffusing out of the active site, or it can disappear via product being formed, okay? So Km is very strongly related to affinity for substrate, but not the same thing. Okay, we can express a value for Km as in terms of the rates of the processes in our conceptual model. So Km expressed in terms of rate constants. From the conceptual model. And more often than not, okay, it's usually measured in the lab, okay? So usually derived from experimental measurements. And so we call that empirically determined, right? We use the term empirical when we're talking about making measurements. Okay. So, the one thing that I had not mentioned in this model, right, is Vmax. Okay, so this is the rate when all enzyme molecules are what we call saturated with substrate. And we use this analogy of the cats with the balloons, right? So your Vmax is going to be, your rate of product formation that you would see, okay, if every molecule in your collection released their product at the same time, which means you can imagine them as, kind of runners who all had the same max speed, all starting from the same starting line. So this is a kind of a theoretical value, okay? It's the rate that would be observed. Okay, so let's change that. That would be observed if all enzyme molecules in a sample released product at once. So what that assumes is that they all started out with product bound, okay? So the point of this picture is to show you that the rate that you would observe, okay, so the number of balloons that you would see released is going to be related to the number of cats that you have there, or enzyme molecules that you have, right? If I have 6 cats holding balloons and they all release balloons at the same time, I'm going to have 6 product molecules, my floating balloons. If I only have 3, I'm only going to get 3 product molecules, or 3 floating balloons. So an important thing about Vmax, okay, is that it is related to enzyme concentration, so total enzyme concentration. So, here our Vmax is going to be, 6 cats, right? It's going to be related to the 6 cats. Here, it's going to be related to the fact that I only have 3 cats. Okay. Now, what really tells you the rate? Remember, when we write rate laws, we have something that relates to concentration. So that's our thing over here, how much enzyme we have there. And then something that relates to rate. And so that's going to be a rate constant. It's going to be a lowercase k. And we use subscript cat, okay? That's why I put the cats in the figure. No, actually, I just thought of that now. All right, so what is this? This is the rate constant for catalysis. So remember, in talking about enzyme mechanisms, and chymotrypsin has, this acts as a general acid, then this acts as a general base, and the water molecule comes in, and we get the covalent intermediate, and when we talk about enolase, we've got all that going on. All those little steps that have to happen. And I said, different enzymes, different mechanisms, those will happen at different speeds, okay? That's all of those steps are what goes into determining, okay, the rate constant for catalysis. So Vmax is the product formation that you see. Okay, it's going to be related to how much enzyme's there and how fast each enzyme can do its job. Okay, what I like to say, I like to say, how good is the enzyme at doing the chemistry? So while in the lab, what we determine is a Vmax, okay? Remember always that depends on how much enzyme you have there, okay? And that the thing that really determines the rate is Kcat, okay? The thing that really reflects those steps is Kcat. Now, if we are trying to make comparisons, we can make sure that we always use the same amount of enzyme, and then we can compare two Vmax values, right? So how do we get these parameters? Well, what we do is we do our experiment, okay, at different substrate concentrations. So you measure the rate at different substrate concentrations. Okay, and then you use that, you determine a V0 for each. Which is, again, the slope of the linear portion of a product concentration versus time graph. Okay, so in the case of what we're doing in lab, you know how quickly that yellow color appears. Okay, so we're going to do this multiple times. Okay, at using a different substrate concentration each time. Then each one of these is going to be a V0, okay, value. So the slope of this line, okay, is going to be V0 for substrate concentration 1. This is going to be V0 for substrate concentration 2, 3, and 4. Okay, so that's the slope equals. Then what we're going to do is we're going to graph the data in one of two ways. Okay, the most accurate way, and the way that we can use now that we have computers that make it easy to do curve fitting to nonlinear functions, okay, is we can plot V0 versus substrate concentration. Okay, this is what's called a Michaelis-Menten plot. Okay, and so our data points, these may be our data points right here. Okay, so those little pink lines are my data points. I use the Michaelis-Menten equation, okay, and notice my V0s, okay, are my Y values, and my X values are my substrates. Now this is a nonlinear curve fit. To this equation. And it yields directly Km and Vmax values. That's what the fit will tell you, Vmax and Km. Okay, Vmax, how good the enzyme's at doing the chemistry, or how good those conditions are for supporting catalysis, right? If you have a pH value that's bad in terms of the protonation state of a catalytic residue, that will slow down your Vmax, because all of a sudden the enzyme, that Kcat, is not as good. That you don't have as many of those side chains in the correct protonation state, so it slows things down. Or you can look at Km and say, oh, under these conditions, maybe there is a residue that needs to be deprotonated in the active site in order to form an ionic bond with the substrate to hold it in the active site. And so maybe your affinity would drop under those conditions, right? And so that then you'd have a different Km value. So the other way of doing this is if the only thing you can do is fit to a line. Let's say the only software you're going to use is Excel, and all you know how to do is a trend line. Okay, what you can do is you can do what's called a Lineweaver-Burke plot, where the thing that differs is that you plot 1 over V0 and 1 over the substrate concentration. So basically what you do to go from this to this, okay, is you just do 1 over the Michaelis-Menten equation, okay? And that leads this Lineweaver-Burke equation. So 1 over V0, right? That's what we plot on the Y, okay? And then equals, and this is written such that it'll look familiar to you. So we've got Y equals something times something plus something. The equation for a line is mx plus b, right? So if we plot 1 over s on our x-axis, okay, so I'm going to change that so that it's clearer, right? So that our y is our 1 over v0, our x is this. Then that means the slope of a Lineweaver-Burke plot, okay, is going to be Km over V max. And the y-intercept is going to equal 1 over V max. So that will enable us to then solve. If we know the equation for the line, we can solve for Km and V max. Now the other thing to note is that this point right here, the x-intercept, is equal to minus 1 over Km. So you could also, solve the equation that you fit to and get Km directly, okay? And we'll practice using that a little bit. So this is what a nonlinear fit to the Michaelis-Menten equation looks like. We're going to use Mathematica or the data analysis app. Data analysis app is easier, and given the time we have, we'll do it that way to fit to the equation. So if you'll notice, so I have some data represented by the dots here, and when I fit that data, okay, it gives me values for my Km and my Vmax, okay? So if we notice, okay, so my Vmax for the first one is 3.999, so let's call that 4. So data set 1, let me match colors here. Okay, we got Vmax is equal to 4.0, oops. And our Km is equal to 1.998, so let's call that 2. Okay, and then for data set number 2, Vmax is equal to 3.997, so that's more rounding that to 4, and our Km is equal to 5.98. Okay. So let's call that, I'm just going to round everything to 6.0. All right. Okay, so let's talk about where Km and Vmax appear on a Michaelis-Menten plot. Okay, so Km, remember this is related to substrate affinity. So this is going to look just like a hemoglobin binding curve in terms of our point of reference. So Km is the substrate concentration, remember, where you have half your maximal rate. So 1/2 Vmax, okay? So if we go to it, we know that our Vmax is 4, okay? So we have not shown enough data. We've not gone high enough in concentration to get to 4.0, okay? So half of that rate is going to be 2. So that is what our Km is, okay? So we've got, let's see, so this is 10, this is 1, 2, 3, 4, 5, so each one is 2, so that's 2.0. And then for our other one, that was, my line is very terrible, that's 6.0, right? So for data set 2, okay, what do we have? We have the curve shifted right, and we have a higher Km value. And what did we say about hemoglobin's affinity for oxygen when the curve shifted right? We said it had a lower affinity, right? It took more oxygen to get it to load. And so what that means is we have a lower substrate affinity. Okay, so this is going to follow the same right shift, left. If it shifts to the left, we're going to say we have a higher affinity. If our Km value is lower, we have a higher affinity. Okay, all right. So that's what so that's what things look like. Okay, in a Michaelis-Menten plot. Okay, now you can't really estimate as easily what things would be, and again, because of equilibrium, your curve is kind of asymptotically approaching Vmax, but you're not actually going to see it in your experimental data. Okay, so the Lineweaver-Burke equation, again, it's called a double reciprocal plot because you're taking the reciprocals of V0 and the substrate concentration at which that V0 was determined. Okay, and it is easier in terms of computationally speaking, but these methods were developed pre-computers, so when working with lines was easier than nonlinear curve fitting. Now the things to note about Lineweaver-Burke. So Michaelis-Menten fitting to the Michaelis-Menten equation. Okay, this is the most accurate way of getting. Most accurate way to get Vmax and Km. Okay, from your data. Okay, however, the Lineweaver-Burke equation. Okay, so doing a Lineweaver-Burke analysis is kind of the best way to visualize changes in Km and Vmax. And so we use this when we're doing trying to figure out inhibitor mechanisms. So I'm just going to put inhibitor mechanisms. You can really easily tell what a chemical inhibitor of an enzyme is doing by looking at how the lines on the Lineweaver-Burke plot change. Okay. Oh, and look I even wrote it on the bottom of the slide here, determining the mechanism of the inhibitors, but it's less accurate for determining the parameters. So we've already talked about how the slope is equal to Km over Vmax, and how the y-intercept is your 1 over Vmax, and how your x-intercept is minus 1 over Km. All right, so what can we learn? So we'll go over what we can learn And then when we return to class, we're going to be doing some practicing of looking at data and graphs and figuring out these parameters. Okay, so catalytic rate constant, that is our kcat, right? Lowercase k cat. And that's called the turnover number again. And it's determined from your Vmax and your total enzyme concentration, which is often hard to know that unless you have a very pure sample of enzyme and know exactly how much you used. But again, that tells you, that is essentially the K2 in our conceptual model, right? So that's K sub 2 in our conceptual model. And so the other thing that we use, okay, is something called, so the turnover number, how good are you at making product? But we have this thing called the specificity constant. That's another measure that we use to compare enzymes, okay? And that is, specificity constant is equal to kcat over your km. And so let's just talk about this, okay? So the higher the specificity constant, the more efficient your enzyme is going to be. Why is that? Okay, well, let's think about it, okay? When kcat is high, so kcat high, it's good at catalysis, right? So a rate constant, the higher the rate constant is, the faster the reaction happens, right? So that number being big is good, okay? Now, let's look at the bottom number, okay? Km, when Km is low, we have a high affinity for substrate. So that being low is good. So if we want a metric of how good an enzyme is, okay, we want it to be really good at grabbing onto substrate and really good at doing the chemistry. So what we do is we combine those two into a single number so that when each one of those things is optimized, our single number is as big as it can be. So the bigger this is, the bigger this number will be. The smaller this is, because we're dividing by it, the bigger this number will be. Okay, so that's why the Km is on the bottom and the Kcat is on the top, because what we want is we want this to reflect how good the enzyme is at doing its overall job. Okay, and its overall job is to make product. And to make product, it has to do two things: grab onto substrate and do the chemistry. Okay, so that's the catalytic efficiency. All right. And this is just a repeat of the slide because, of course, I like cats, and I like cats with balloons even better. All right. Okay, so to put this in a little bit of context, okay, let's combine the fact, okay, that we've looked at the steps that we need for mechanisms, and those involve, so our mechanisms, catalytic mechanisms, and substrate binding, so catalytic mechanism, kcat, substrate binding, Km, they both might depend on pH, right? Because you might have a residue that needs to be in a certain protonation state, okay? So if we look, okay, we can look, every enzyme is going to have its own pH profile, okay? So the enzyme pepsin, this enzyme is found in the stomach, okay? So at low pHs, stomach pH around 2, okay? And so what you'll notice is that that enzyme is optimized, okay, to work around a pH of 2. And when you get above or below that pH, activity drops down because, the active site is no longer in its optimal protonation state, okay? Whereas if we look at other enzymes that work in different environments, okay, they can have even basic pHs as their preferred environment, okay? So that's why last week in lab, the first thing we did was try to determine which pH this enzyme worked best at. Okay, so, and then the other thing is temperature is going to affect activity. So what does temperature affect in terms of the active site? That would mean that something like Taq DNA polymerase, which Taq is from a thermophile, which means heat loving. So this is, from an organism that lives in a very hot environment. And E. coli, this is just a normal at body temperature. Okay, it's optimized for that because it lives in our colon. All right, and so temperature, okay, is going to affect movement, right? Higher temperature, faster movement. Okay, so it affects flexibility. Okay, now, so these two molecules, okay, they catalyze the same reaction, but one of them works at body temperature, the other works at 80 degrees Celsius, almost boiling, okay? And the difference is going to be how stiff the structure is, okay? So you can imagine that the Taq DNA polymerase, okay, has a structure that's stiffer and less flexible, okay? And there may not be enough thermal motion for the mechanism to work at body temperature, but once things get heated up more, okay, then the structure still stays intact, but the flexibility it gains with that thermal motion enables it now to kick into its active state. Whereas with the E. coli, okay, it's going to be a less stiff structure. It's going to be a little looser and less stabilized, which will enable it to work fine at 37. But when you increase the temperature, that structure is not going to be able to hold the active site in place. Okay, so you may have residues that are too far apart to do what they need to do. Okay, so we're going to do some practice questions next time we are in class, and I'm going to record another video about regulation and how we use kinetic measurements to study enzymes.